Okay, then let's start with the DC circuits. Without any delays, there will be four things that we are going to discuss about. First is series circuits. Like what kind of circuits are known as series circuits, right? What are their characteristics? Same thing we'll do with parallel circuits as well. Like both of these are pretty easy to start, but once you understand these two things, it would be a lot easier to discuss on something known as Kirchhoff's laws. These are very famously known as KVL and KCL. You might have heard about that. It might be really confusing for you as well, maybe, right? But once you know the first two, third becomes really easy, right? And finally, we will try to conclude the whole DC circuit by understanding what is electrical power, how does it flow, and things related to that. And finally, concluding by understanding about the energy, electrical energy in general. Okay then, first series circuit, right? So here you can go through the definition. Meanwhile, I will just focus on the highlights. So right now we are talking about resistors. It's fine to talk like that, but in general case, the resistors might be replaced with some kind of load, some kind of element, but the gist still remains same. So for simplicity, I'm using the term resistors, right? But you can make use of anything as an element. This thing might confuse you, so let's stick to very simple fundamentals. Let's not confuse ourselves, right? So how should you know a series circuit is a series circuit? One major difference comes from how the resistors in the circuit are connected, right? Or the elements in the circuit are connected. If they are end-to-end connected, right? And along with it, if they are connected such that they will form only one path for what? For the flow of current, right? So there is a current I that is flowing through that single path, end-to-end connected resistors. So this is known as end-to-end connection, right? So if there is a single current that's flowing through this circuit, then we'll call that circuit as series circuit. And we'll say that, okay, these resistors are connected in series like this, right? How are they connected? They are connected in series. And what is this circuit known as? This circuit is known as series circuit. Very basic, right? I hope you understand. So focus of the point is there should be a single current that is flowing through all of them, and it should be same single value of the current. So let's look at this circuit first. There is one resistor connecting from point A to point B, or let's say point A and point B are connected with the help of this resistor in between them. Similarly, point B and point C here, the terminals, there is something in between them, which is resistor R2. Similarly, point C cross point D, in between there is something R3, right? So these are some resistor values. For example, this might be 1 ohm, that's resistance, right? This might be 1.5 ohms. This might be again 1 ohm, right? It might be anything. For now, we are just generalizing, right? So we understand this is an end-to-end connection just by looking at the terminals and how they are connected, right? Now you would add that circuit to some source, maybe. It might be a battery source like this, right? We'll know that by looking at the terminal. It's a plus and minus this way. And that source has a voltage, capital V. Now, there should be some current flowing through it because this is a closed loop. And that's the definition of electrical circuit, right? Now, there's a closed loop. There are some elements connected in that circuit. There's a source, so there must be some current flowing through it. That current is capital I. And if you look at it just from observation, you can say that there is a single path and nothing else. So, a single path means the path for the current. It's traveling through R1. The same current is traveling through R2. The same current is traveling through R3 because there is no alternate path, right? It's pretty simple. That means at point D, the current coming out must be equal to I, because there was no branching here, or maybe here, or maybe here, right? There was no branching. So just a single path, it came out again as capital I, which makes sense, and returned to the source, right? So coming out of the source, capital I, returning to the source, capital I, preserved, right? Now, if you understand this thing, the basic flow, let's not make it complicated. Let's understand one by one. So you understand what's R. You understand these terminals, how they are connected. You understand what's the circuit doing here, and what's this? A source, right? Now, there's something here, which I have noted as V1, right? There's something here as well, V2 and V3. Well, the subscripts, they make sense. 1 for 1, 2 for 2, and 3 for 3. Very easy. But what does this mean, V1? So V1 just means that there's a potential across this, but the better way of saying it is, what's a drop across this resistor? So the term is voltage drop, and we use this word drop like frequently. You will hear this very, very frequently if you are new to electrical engineering, right? This is more associated with something known as load, or let's say it's like a consumption, right? Forgive me for any spelling mistakes. But if there is something like resistor, which is a passive element in general, right? Such loads will consume things, right? And when we are talking about electrical circuit, they literally consume electrical energy, right? So when you talk about potentials across the point, most of the time you are talking about the drop that happens across that. Or in another word, if you want to carry some energy from this point to this point, there will be some loss in energy because of that element. And whatever is lost is kind of given in terms of voltage. That's how definition of voltage is actually set. And definition of voltage drop comes from same thing. So if I can explain you, I would just say that V1 always exists across R1 or between the two terminals here, A and B, and it is known as the drop, the voltage drop across this resistor R1, and we're calling it V1. Similarly, there's R2, so there must be some kind of drop, voltage drop associated with R2, and we'll call it V2. Similarly, there should be some voltage drop associated with R3. Now, this voltage drop actually depends on the value, right, of the R3. If R3 is 1 ohm, it would be something different. If it is 3 ohms, it would be something different, right? Let's just understand this much first. So what are V1, V2, and V3? These are voltage drop associated with those elements respectively. And the subscript explains that, right? Okay, great. Now, let's not forget about the Ohm's law. So if we recall the Ohm's law, that's V equals to IR, right? V is that voltage. It can be drop, it can be the source, it can be anything, right? But if it's a voltage, it should satisfy something, a relation like this, I times R, right? R is the resistance or the resistor value. I is the current flowing through that element. If there is current flowing through here, we'll note that down, that I, and that value itself. Now multiplication of these two, right, shall give us the V that's associated with that element. Now, it's not something else. If we are talking about R1, we should be we should think about the current flowing through that, and it will give us the V that is associated with that R, particular R. So it would be different for R2. It would be very different for R3. We should keep that in mind, right? So if that is understood, what I can write is the voltage drop across this particular element R1, I can write that by recalling the Ohm's law. Since the name is V1 for that, I would write V1 equals to current flowing through it. And definitely there's only one path for this current that we have assumed for the whole circuit. Yeah, that is definitely going through R1. So the current flowing through R1 is I, correct? So times R1, that comes from Ohm's law. Why I'm writing R1? Because we are trying to calculate that V1 for R1. So V1, voltage drop across R1, is given by the name V1, which is equals to the from Ohm's law, I times R1, right? In the same manner, voltage drop across this resistor R2, that would be given by V2, this across R2. Again, current flowing through it. It's the same current flowing through R2 again. So it's the same current I, R2, right? Similarly, the same case happens for R3, the drop across R3, right? Or just simply the voltage across R3. Capital I again, because the same current flows here, right? R3. As simple as that, nothing confusing, right? So we have three relations built here, V1, V2, and V3, right? And we know it's IR1, IR2, and IR3. Okay, cool. Now, if we understand that, let's see this. Okay. Now, the way we dealt with R1 and voltage across it or drop across it, R2, drop across it, and R3, drop across it. Now, what is the drop across terminal A and terminal D as a whole? This was across terminal A and terminal B, V1. Across B and C, V2. Across C and D, V3. Well, cool, nice. But what's the voltage drop across A and D then? Just think about it for a moment. That drop across this and this, potential across A and D, is indeed V, because this point is same as this point, and this point is same as this point, isn't it? This is a short path, right? You can observe that, and you can say it's V. So what potential is across A and D? You can say, like, you can form the theory, like the language like that, right? And you can say, oh, well, yeah, it's V, because across this and this makes sense. Across this and this makes sense. Across this and this makes sense. Then across this and this also makes sense. Right? Okay then. So V, okay, then it should be sum of these three, isn't it? If I'm talking about these 2 points, then it should be the sum of this, this, and this. So let's think voltage drop as some kind of loss. Then loss over here across this, or loss over there across this, and loss over here across this can be added to account for loss while going across A to D, right? Something like that. Okay, so V by observation can be seen V1 equals to, V1 plus V2 plus V3. That's true. Now, V is a little bit tricky because we said before this is a source. Well, that's true. It can be a source, right? Because we are talking about the I that's flowing through here. There must be something driving that circuit, right? So let's not go into very depth and let's confuse ourselves, but let's just see it simply. So V equals to V1, V2, V3. The sum of these three makes sense, right? Now we know V1, V2, V3. We just calculated that. We can actually substitute that. So this line is actually pretty clear. I can take I common. Pretty interesting, yeah? Okay. Now I can take this on the other side. So it would give me V divided by I. I will be left with R1, R2, and R3 sum on this side. Now, what is interesting is capital V is kind of the voltage across the whole circuit. The whole circuit from A to D, right? This is what is closing the circuit. V is of the whole circuit. It's the voltage across the whole circuit. Like, let's use this language. Similarly, capital I is also associated with the whole circuit. Is the current flowing through the whole circuit, right? Voltage across the whole circuit, current flowing through the whole circuit. Now, this is something that is very familiar. That is V equals to IR. We can rearrange that and form V divided by I, which is eventually the resistance R. Okay, that means we can write this in terms of R like this. And this is really unchanged, right? So what we have just written here is also R, right? But see, in the circuit, there is no fourth resistance. We have already written R1, R2, and R3. And sum of these three resistors is already here. Now, what's this fourth R? What's the story about this? Now, this is something which we write generally as Req, saying that it is the equivalent resistance of the whole circuit. How the story forms is because V is for the whole circuit, I is also for the whole circuit, then whatever this will give should be also for the whole circuit, right? This thing should be for the whole circuit. Not some individual elements, but for the whole circuit. If I have to find equivalent resistance of all these three, I will call that Req, right? That's for the whole circuit. Make sense? Since these two elements were for the whole circuit, this should be for the whole circuit. And since it's something that's virtual or derived, we'll call it R equivalent. And the relation holds that R equivalent is R1, R2 plus R3. Got it? Yeah. So it's equivalent resistance of the series circuit. Since the derivation came from a series circuit into interconnected resistors, we'll call this relation, which is true for series circuit. It's equivalent resistance of the series circuit. Now the fun thing is, for any number of resistors, for n number of resistors, it's still true, right? So on Rn. Doesn't matter. If there are 10 number of resistors, you will add all of them, right? And you will get the equivalent series resistance. So the term is equivalent series resistance. This is really important, right? So this is one of the important derivations you should know. So if you are solving a circuit, electrical circuit in particular, you should be able to write equivalent resistance of that circuit so that it becomes a lot easier for you to find unknown parameters. Let's say there is I, there is V that are known. Sorry, there is I you need to calculate. Let's say you have a source DC battery, let's say 12 volts known, right? And let's say you have these individual R known. For example, this is 1 ohm, this is 2 ohm, and this is 3 ohm, something like that. Now, since voltage is known as 12 volts, someone asks, what current is flowing through the circuit? Like, what's the magnitude of that current? So you will certainly remember the Ohm's law. It says V equals to IR. Okay, I should be able to calculate things from here because you know V. Someone is asking what's I, but this thing is missing here. What's R, right? So what you will do is you will quickly say, okay, Req for this series circuit, because this is a series circuit, it must be R1 plus R2 plus R3. Well, that's known. Now 1 ohm plus 2 ohm plus 3 ohm, right? Now you will find what ohm this is, right? So 3 plus 2, 5, 6 ohms. Great, you know Req now. Come back here, put it here. Now you will find I equals to V divided by R. Now V is 12 volts divided by Req, which is 6 ohms, right? So 12 volt divided by 6 ohms. This is how you get your current flowing through the circuit. 6 to the 12, so 2 ampere is flowing through here. I hope I've not complicated things, and I'm really hoping that you understood the logic, right? It's pretty simple. If you just look through this, just by observation, you can find out a lot of things here.